Equilibrium is a place where you reach a point in a reversible reaction, so it has to be reversible, and where the products and the reactants remain constant. So you reach this magical point where, yeah, some reactants are turning into products, and some products are turning into reactants, but there's no net change. This is the idea. You need to be able to describe each one of these. Number 2, simple. Number 3, if you can do number 2, great. Number 4 is mathematical. Number 5, simple. And then number 6 is a specific example of equilibrium called the Haber-Bosch process. Equilibrium is the idea that you have a system and it's sitting in equilibrium. If you change something, then the equilibrium will have to shift. So if you apply a stress or if you put in some kind of a change, the system will shift and reestablish equilibrium. I know that's kind of ethereal to think about and kind of hard to think about, so I have an awesome picture for you. All right, so what do I have here? I have a fish tank, and in this fish tank, we are some fish. Why do I have fish in there? Well, because it's a fish tank, and but the fish are unimportant. The important part about the fish tank is right here there is a divider. What's important about this divider is that I can make it go up or down, but I always have to leave a gap underneath here. So this will allow water to flow. On the left, I've got R, meaning reactants, and on the right, I've got P, meaning products. So this is kind of the setup of a chemical reaction. Now, I've got equal levels of water on both sides. So we would say this is at equilibrium. Okay, let me give you an option. Is this system at equilibrium? You're right, no, because there are way more reactants than products, and so some of this water will flow down through the bottom of the gap and over to the other side. And what will the new equilibrium look like? Well, the reactant side will go down. We're going to use up some reactant. The product side will go up because we'll make some product. And we will reestablish an equilibrium. So Le Chatelier's principle says if you stress it at all, then it will establish a new equilibrium. So let me go ahead and stress it. I'm going to add a bunch of product to this side. Well, wait a minute. I stressed it. Is this system now at equilibrium? Well, of course it's not. The water levels aren't the same. So what if I just make them equal? Meaning the reactants go up and the products go down. It reaches some new equilibrium. Well, that makes sense. I can live with that. Okay, so that is the basis behind equilibrium. Now, the important thing is these are reactions that are reversible. So you might have a reaction where you do this, where you get a whole lot of product and not very much reactant. So I can move the divider left and right. I can also do this. I can say, wow, I'm going to make very little product and just have a little bit of product and a whole lot of reactant. They're still at equilibrium because the water levels are equal, but usually we'll just go, okay, well, what if they're just right down the middle? So that is the basis behind equilibrium. So real quick, let's go over and flip through what kind of changes can occur. So if you change the concentration at all, if you add a component, it will shift away from that side and towards the other side. So let's look real quick. Okay, so I add some reactant. Which way is it going to shift? Is the liquid going to flow from the reactants over to the products or from the products over to the reactants? Well, if you said the latter, then you've been smoking crack because the water will go from the reactants over to the product side. So this one will go down a little bit. This one will go up a little bit. And ta-da, there you go. What else is there? Temperature. If the temperature changes, then equilibrium will change based on if it's endo or exothermic. Okay, so let's go look at that one more time. So let's say it's endothermic. What does endothermic mean? Well, endothermic means that heat is a reactant, right? So Heat goes into the reactant side. So what do? Well, think of it this way. What happens if you heat up this reaction? Well, if you heat up this reaction, we're adding a reactant because we're heating it up. So we will get the reactants go down and more product form because heat is a reactant. What happens, though, if that heat is a product? What if it's exothermic? What happens now if we heat it up? Well, it's the same thing as before. If you add something to one side, because heat is a product over here, then it'll make a new equilibrium by turning some of that product into reactant. So heat is just like anything else. Heat will make it change equilibrium. So if you ever add an inert gas, and this is something to look at and make sure you star it in your notes, anytime you add an inert gas, what does it do to the equilibrium position? Nothing. It's like adding another fish to the fish tank. So if I added a fish doesn't do anything to the level of water. If you add pressure by decreasing the volume, it'll shift it towards the side with fewer moles of gas. So this is something to keep in mind. When you add pressure, it shifts to the side with fewer moles of gas. What if in the reaction, neither side has fewer moles of gas? Then it would have no effect. But if you decrease the pressure, so do the opposite, what happens? Well, if you decrease the pressure, then it will favor the side with more moles of gas. So let's go back to the fish tank real quick and just walk this through. Let's get rid of our heat for a second. We're done with that. Let's bring the water level back up. What happens if I add another fish? Well, let's add another fish. Duplicate. Where's duplicate? Duplicate. Clone. So I added another fish. What does that do to the equilibrium? Nothing. That's like adding an inert gas. It does absolutely nothing to the liquid level in there. So what are my possibilities? Let's say I cut a hole right here. So let me come up here and grab an eraser. What happens if I cut a hole and I take some product out? Which way will the water flow? Well, hopefully you know that water flows this way. Whee! So when you take something away from one side, it favors that one side. What else could I have done? All right, well, let's say that I add some product. Whoop! What happens? Well, it would flow that way. That just makes sense. So when you add something to one side, it flows to the other side. When you take something away from that side, it flows towards that same side. So let me write a reaction real quick. Let's go N2 plus H2. Those will be my reactants. And over here is NH3. This is how we make ammonia. This is a reversible reaction. Okay? Now it turns out that this thing right here makes very little product. So to be truthful, we just need to come over here. So we have more reactants and less product when this thing runs. Are we still at equilibrium? Yes. What happens if I add a catalyst to this? A catalyst has absolutely no effect on equilibrium. So what does the catalyst do? Just makes it happen faster. That's it. That's it. So when you add a catalyst, it has no effect on equilibrium. It just makes it get there faster. So you add a catalyst, it goes faster. You take away that catalyst, it'll of course go slower, but it does not affect equilibrium. It doesn't affect the overall water level. Now let's say you added pressure on this. Well, to do pressure on this, now I got to balance this sucker. So let me move this out of the way, and let me go ahead and balance this sucker real quick. So I'm going to put a 2 here and a 3 here. So let's say you added pressure. Which side would it favor? These are all gases, by the way. What side would you favor? You would favor the side, that's right, you would favor the side with fewer moles of gas. It's like putting y'all all in one big room. You kind of get crowded and you want to leave, right? So imagine if you could take 40 people and magically change them into 10 people. Wouldn't that make things less crowded? Well, that's exactly what it's doing. I got 4 moles of gas over on the left-hand side. So if you jack up the pressure, it's going to favor the side with fewer gas molecules. So if I increase the pressure, it'll flow over to the right. We'll get more products formed and less reactant. So keep in mind the idea of a fish tank. If you can do a fish tank, then you can understand which way it'll flow. Heat is the same as any reactant or product. whether it's exo or endothermic. You just got to consider that. If we have an equation, A plus B makes C and D, and notice that double arrow, the C and D can turn back into A and B, we can write an equilibrium expression where K is the equilibrium state. Sometimes you write it as K, sometimes you write it as KEQ. I've even seen it write KC, but they all mean the same thing. How do we write that equilibrium expression? It is so simple. To write equilibrium, it's always the products, the concentration of the products over the concentration of the reactants. This time we get exponents not from experimentation, not because Moses came down from Mount Sinai. We get those exponents from the coefficients. So this 4 came from here. This 6, sorry, that 4 didn't come from there. That 4 came from here. Whoops. That 6 came from there. This 4 came from there this time. And this 7, roundabout, came from there. Okay? We always write products on top, reactants on the bottom. We never include pure solids or liquids because you can't have concentrations of pure liquids. How concentrated is pure water? It's all water. How concentrated is salt? You mean in water? No, in just hard salt. There is no such thing as concentration of salt when it's dry. Okay? Has to be a solution of some kind. So we're not going to be talking about, we never put solids and liquids in there. Only solutions and gases because they're the only ones that can have concentrations. You can also write an equilibrium expression for gases. Like let's say you weren't doing molarities, like where you would use those lovely brackets that we're used to like that. Let's see that you had gases. Well, it would be the products, the pressure of the products over the pressure of the gases on the left. So you can write a KP where you put products over reactants. The coefficients still are used for exponents. You just use pressures instead of concentrations. That right there, that's an equilibrium. That would be K. There is another thing out there called the reaction quotient. And the reaction quotient is a way to tell if something is at equilibrium. It's a mathematical way of determining, based on initial concentrations, is something at equilibrium. For instance, you can look at this and tell it's not at equilibrium. Why? There's a lot more products than there are reactants. Well, so you can look at that and tell, but you can't always look at a chemical reaction and know. So the way you do it in a chemical reaction is you write a Q expression. Notice, it's the same thing as a K expression. K is what the value is at equilibrium. Q is what is the value right now. I want to know whether we're at equilibrium or not. So based on that, you can go, oh, this is my initial concentration of HF. And this is my initial concentration of H2 and O2. And based on that, I can figure out whether or not I'm at equilibrium. See you in the next podcast.